Thank you all for coming to this meetup. We're going to start in about a couple of minutes. But first, we're going to have a word from our host, GetYourGuide. So I may call you on stage. Thank you. Let's go.
Hi. Amazing. It's so great to see everyone here. Thanks so much for coming. My name is Katrina. I'm an employer brand manager here at GetYourGuide. Finishing up my last few weeks before maternity leave. So happy to be doing this before I head out. What can I tell you about us? What are we all about? We want to fill people's lives with moments of discovery and wonder. And what that means in practice is that we unlock the world's most unforgettable travel experiences. That means you can use our platform to find really, really incredible things that you can't do anywhere else, such as, going sandboarding in Dubai. One of my favorite originals tour that we offer is in Rome at the Vatican. You can actually unlock the Vatican Museum with the key holder at 6:30 in the morning, something like that. So some really incredible things. And what we are working towards is we want to be the leading global marketplace for travel experiences. And what that means is we're defining a new category of a marketplace. So when you think, what should I buy? You think of Amazon. When you think, what should I watch? You think of Netflix. Where should I stay? Airbnb. And what should I do? GetYourGuide. And just some key figures about us that we're quite proud of. We have over 800 employees, about 500, probably more now in Berlin. We've sold over 150 million tickets to date, coming up on our 15-year anniversary, actually. And we have 17 global offices worldwide, working with over 25,000 suppliers, which is pretty cool. Those people are small businesses, and we're helping them, build their businesses on our platform. So if any of that sounds interesting to you, we are hiring, shameless plug. So we're looking for ML ops, kind of always. So please check out our career site, as well as data science roles. If you have questions, let us know. And otherwise, I'll hand back. Thank you so much.
Thank you. Thank you again for GetYourGuide for this amazing venue. We're going to start soon with the first talk. Morena from GetYourGuide will actually give the first talk. So Morena is a data scientist at GetYourGuide. She's also the co-organizer of the MLOps community meetups, which you might have seen already here in the past. Today, she will talk about facts versus fiction, autodetecting hallucinations in LLMs. Morena, you may come on stage.
Okay, hello everyone. Thank you for joining. For the next 30 minutes, I will be talking about auto-detecting hallucinations in large language models. But I would like to start off first with a little game. So the game goes as follows. I will give you two statements. One is completely BS, and the other one is actually a true fact. And then you guys need to guess what is true and what is completely made up. Okay, here we go. The first one is Justin Bieber's DNA was sent into space aboard a SpaceX Falcon 9 rocket in 2021 as part of a promotional collaboration between Bieber and a technology company. And the second one is, in the 1980s, Saddam Hussein was given the key to the city of Detroit after donating $250,000 to a local church. The church's pastor, Jacob Yasso, calls the former Iraqi president a very you can't Google, obviously, by the way. Like, don't ruin the game. So Jacob Yasso calls the former Iraqi president a very generous, warm man who just let too much power go to his head. So who thinks the first one is true about Justin Bieber and the second one is false? Raise your hand. Okay, yeah, you can lower your hands. And who thinks the first one is false and the second one is true? Okay. So I can tell you that the people who raised their hands second are right. The Justin Bieber one is completely made up, and the Saddam Hussein one is actually true. These are both statements generated by ChatGPT. One is simply hallucinated, and the other one is true. As you can see, it was like relatively even. So just to show how hard it can be sometimes to detect these hallucinations, right? Okay, so before we move on, let me just introduce myself. My name is Morena. I work as a data scientist here at GetYourGuide. And I also am a co-organizer of the MLOps community meetups in Berlin, as Stefan just said. I don't have a lot of time and I have a lot to tell, so let's go. I will first talk a bit about the what. So what do we actually mean when we're talking about hallucinations in large language models? Then I will go a bit into the why. So why do we see that these large language models have this tendency to hallucinate? And then I will go over a couple of methods to detect these hallucinations and hopefully have time for a little demo of one of them, and then I will end with a summary. So, as we know, these large language models have shown tremendous potential across society recently, but their tendency to make stuff up kind of makes them unreliable in a lot of cases to deploy them in production. And what do we actually mean by these hallucinations? So the formal definition of it is the generation of content that is either factually incorrect or nonsensical or unfaithful to the input context. And we can distinguish between two types of hallucinations. The first one are intrinsic hallucinations. And here we're talking about generation of content that is directly contradicting the source material. And the source material in this context, what that is, can differ from use case to use case. So if we're talking about a QA task, like a chatbot, a dialogue task, then the source material is basically all world knowledge. If we're talking about text summarization, then the source material is referring to the input context that you give the LLM to summarize. So in case of the intrinsic hallucinations, it's directly contradicting that. And in the case of extrinsic hallucinations, and these are a bit trickier, it's content that is not directly verifiable by the source material. So to give a bit of an example, if we have a task to give to an LLM to summarize the Wikipedia page about Paris, then an intrinsic hallucination can be that it says Paris has a population of 1 million residents. This is directly contradicting what's in the Wikipedia page about Paris. But an extrinsic hallucination can be something like Paris is home to the most successful soccer team in France. It's not directly contradicted, but it's also not directly supported, and I can't verify it using the Wikipedia page. And these are the tricky ones, right? This is where it's getting hard to detect them, and also the ones that are mostly the most harmful, actually. So as you can understand, these hallucinations can be harmful in many ways, like I said, especially if it's hard to verify the information. And this forms a major challenge for deploying these LLMs in production. And even more importantly, it's potentially harmful for society, right? If you look at the areas where these LLMs are actually showing the most potential, or at least I personally think that healthcare, for example, is an area where they show tremendous potential, being able to make medical knowledge accessible for a way broader population than has been the case so far. But at the same time, if they start to hallucinate medical knowledge or even treatment recommendations, then can be very dangerous. And I will get a bit into this in a bit, but the nature of these models also makes that they output this false content in a very convincing way, as you saw with the game earlier. And yeah, all this makes it increasingly important to detect these hallucinations in a structured and quantitative way. But why do these LLMs hallucinate? Why do they have this tendency? The first important thing here is the training data, right? The data that it's trained on. If this contains contradictions or false information, then it's hard for the model to detect these patterns, and the probability that's going to hallucinate is bigger. And because these LLMs are trained on gigantic amounts of text, there will be contradictions, right? There are LLMs that are trained on all text on Reddit, and I hope we all know that not everything on Reddit is accurate. So yeah, then you're introducing contradictions in the training data, and that could be a reason for hallucinations. Another thing, a factor that's very determining for the extent to which an LLM hallucinates is the complexity or the novelty of a task. So the complexer the task, or the more unseen a task is for an LLM, the higher the probability it will hallucinate. But I think the most important thing here to understand these hallucinations is to understand a bit better how these models work. So the fundamental autoregressive nature of these models. Because these LLMs are generally trained to predict the next token in a sequence in a probabilistic way. So what happens is it just breaks down the text into tokens, and then it predicts the next token in the sequence based on some position and token embeddings. So just to go back a little, to emphasize, this means that these models have no notion of ground truth. If they output something correct, they know that it is probably correct, but they don't know why it is correct. And this is an important thing to understand. It's just operating on data-driven patterns, right? So if you give an example, like this sentence, Cristiano Ronaldo is A, if you want to finish this, then it breaks it down into tokens, which are then parts of words. And then it tries to find the token that should come next with the highest probability. And in this case, footballer will have a very high probability because Cristiano Ronaldo is very famous and he appears a lot in the training data. And other professions like politician or scientist will have very low probabilities. But as you can understand, in case of a task that is not as common, this probability distribution is going to be flatter, meaning that the entropy is just higher. So the probability that it will choose something that is wrong is just going to be higher, right? Okay, now we can go into the different detection methods. So I went through some papers. There are quite a lot of things out there. I tried to summarize them in 4 categories. These are not mutually exclusive, like some of these methods are a combination of these categories. And then I will give like an example of an open source tool you can use for each of them. And then I will like quickly go into, for each method, kind of what they're based on. So the first one is self-evaluation. This is where you basically prompt an LLM to evaluate its own response. And this is actually what Phoenix Evals uses by Arise. The second one are reference-based methods. So these measure some kind of inconsistencies between the response and some reference text, depending on the task. It depends on the task what this reference is. And an open source tool that uses this is Bragas. I actually have no clue how to pronounce that, but you can click on the link. I will share the slides, by the way. And then there are uncertainty-based methods. And these actually leverage what I just mentioned about these tokens. So the idea is that if you have access to the model and you can use these token probabilities, then you can kind of find out where the model was less confident. And that is also a higher probability that it's hallucinating in those cases. GEval is an example of this. And then there are consistency-based methods. And these use stochastic sampling of responses to then try to find inconsistencies or similarities between these samples. And an example of this is self-ChatGPT. So let's go a bit into these self-evaluation methods, because the first time I heard this, I found this very counterintuitive, that you let an LLM evaluate itself. But the idea behind this is what I mentioned earlier about that the complexity of the task is very much influencing how much the model hallucinates. And in general, like summarizing a text is a lot more complex for an LLM than saying, I have this output and this input, is that inconsistent with one another or not? That's a relatively easy task. So this self-evaluation capability you can actually leverage for an LLM to detect its own hallucinations. And what this would look like in terms of a text summarization task, for example, is you prompt the LLM and you say, summarize the following text. And then you break down this response into sentences. And then for each sentence, you prompt the LLM again, saying, hey, this is the context, so that's then the input text. Does this sentence support this context? Yes or no? And you can also use this in combination with other methods. This example actually is a combination with reference-based methods, right? Because in this case, you give it a reference, which is the input text. And then you can also use it in combination with these consistency-based methods, which I will go through later, to make them a bit more robust by sampling it. Then the reference-based method. So Here you measure the generation consistency against a provided reference. These are not always available, right? It really depends on the use case. If you have a reference, in case of an open QA, for example, this is going to be tougher because there is no reference directly available. You see tools where they use benchmark data sets as a reference, but it's just not as straightforward. In use cases of RAG, you can have references available through retrieval. Can be a bit noisy because you need to retrieve them as well, but it's possible. But the best use case for this kind of detection method is text summarization, because you give the reference with the prompt, so it will be available and it's easy to use. So what happens is you basically, again, you break down an LLM response into sentences, and then for each sentence, you calculate some kind of similarity score between the sentence and this reference. And you can use different kinds of scores for this, like BERT score or Rouge. There are also cases where they use like natural language inference kind of scores. There are loads of scores out there that basically measure text similarities. And then you can leverage that to see in which sentence is it contradicting this reference or not supporting it, and flag those as hallucinations. Then these uncertainty-based methods are methods that use the internal states of the LLM. So what I mentioned earlier with the token probabilities, if you have access to those, then you can leverage them to aggregate them in some kind of way to see where in the response was the LLM less certain, less confident, and you can use those to flag these hallucinations. These require access to token level probability distributions, though, which I think GPT-4 does now with the log props, but I don't know. The thing with this is if OpenAI decides to deprecate that tomorrow, then your whole method is gone, right? But yeah, if you have an open source LLM, this can work well. So the idea is here that you have a sentence, and you can even on token level predict where was it more certain, where was it less certain based on these log probabilities. And in this way, you can flag the tokens where you think it's hallucinating. I will share the slides, by the way, if you need them later. No worries. Then the consistency-based methods. These are methods that are using this idea. So if an LLM has knowledge of a given concept, and if it's confident about that, then the sampled responses are likely to be similar and contain consistent facts, right? If I ask an LLM the same thing 5 times and it's going to tell me something different 5 times, then I'm not going to trust it. But if it's saying things that are similar, or at least not contradicting one another, then you don't have to flag it as an hallucination, at least. An example method that uses this is self-check GPT, and it works as follows. You draw a response from an LLM, and then you sample a further n stochastic samples using the exact same prompt. And then for each sentence in your response, again, you measure the consistency. And here you can again use a BERT score or an NLI contradiction score, or even this self-evaluation that I mentioned earlier. You can integrate those methods and say, hey, I have this sentence, and I have this sample. Are these 2 things contradicting one another, yes or no? And then you can just aggregate these scores to create. So what they do in self-check GPT is they create a hallucination score that is close to 1 if they think it's hallucinated, and is close to 0 if it's grounded in valid information. So then you can see per sentence, where do we suspect hallucination? And I actually prepared a cheeky little demo for that. So just to show you how that works, I created 3 prompts. Can you see this? Better? No? Yeah? Okay, I created 3 prompts. One is, give me 3 facts about Cristiano Ronaldo. So here I expect the LLM not to hallucinate, right? This should be very, very obvious in the training data. And And then the second one is give me an absurd fact about toasters. This one is a bit sneaky because it's a bit speculative, so I'm curious what it's going to do with that. And then the third one is, in what episode of Seinfeld did Kramer buy a giant hat? So Kramer never bought a giant hat. So I don't, I'm curious what it's going to say about this. Then I just sample an answer to each of these prompts. And then I break it down into sentences. Nothing magical going on here. Yeah, so this is then what it looks like. It's just a list with the three sentences in the prompt and in the response, sorry. And then for each of them, I sample 3 more responses. The paper says that 3 should be enough already. So I sampled 3 extra responses. And then you can already see that, for example, here for the Ronaldo one, it's quite similar, right? So the first one, it says something about prolific goal scorer, blah, blah, blah. The second one, this is also coming back. So that looks good. And then for the toaster one, the first one is about a computer case that's also a toaster. And the second one about the world's most expensive toaster. So things that are not really directly contradicting one another maybe, but not so sure. But for the Seinfeld one, you can see that it's just contradicting itself. So the first one, it says, the first one is called the Andrea Doria, the episode. Then for the second one, it says he never bought a giant hat in any of the episodes. And for the third one, it says he bought a giant hat called the Urban Sombrero in the foundation. So this is just contradicting, right? Okay, then I just put that in a data frame. And then I use this self-check GPT tool using the natural language inference scores. This paper actually suggests a couple of different scores. You can also use a BERT score with it, but this one is recommended. And then you can see that it gives a score for each sentence. And for the Cristiano Ronaldo one, these scores are not close to 1. For the toaster one, it's already quite high. So yeah, there you can already see that it's going more towards 1, towards the full hallucination score. For the Seinfeld one, you can see that the first sentence is flagged as total BS, basically. So this is just not true, and it already found that out. And if you look at like the median hallucination scores, you can see that the Seinfeld one is very, very close, or yeah, relatively close to 1. The Ronaldo one is pretty okay, and the toaster is also not looking great. So using only 3 samples, it is already flagging some of these hallucinations. Yeah, so to wrap it up, I went a lot faster than I thought. These self-evaluation methods are simple and straightforward to use, and they are useful for a variety of tasks. What I don't like about them is that they're not very suitable for extrinsic hallucinations. These are the hallucinations that you can't really verify, and there I wouldn't use an LLM to do that because they are just not as good as in that. For the reference-based methods, it's very useful for text summarization or RAG cases, but they require these references to be available, and they are not always available. Then you need to work with some kind of human annotated benchmark data set, not great. So for OpenQ8 tasks or free text generation, you can't really use it that well. The uncertainty-based ones are useful for actually quite a lot of tasks, but they do require access to the internal model state. So if you have an open source LLM, sure, this can work. If you're using OpenAI or something, yeah, then it's just a bit shaky because, again, if they deprecate it, then it's just, that's what it is. For the consistency-based one, I like these the most because they're reference-free and they work also for black box LLMs, meaning that if you don't have any access to the model itself whatsoever, you can still use them. But they can be challenging in real-time use cases because you need to sample these responses. At the same time, if you do this in parallel or something, it could be solvable and you could still use it. but it's not useful for all tasks. For free text generation, for example, I don't really see a use case. So yeah, it basically depends what your use case is. There are some methods out there. I think the most important thing is these LLMs will always hallucinate. So even if you mitigate it, you will always need to make sure to detect them if you're using it in production, in scenarios where it could be harmful if they hallucinate. And again, I listed all my resources and all the links to the open source tools. So it's, yeah, you can use it as a summary for these detection methods. Any questions?
Thank you, everyone, for the opportunity. Any questions? We had one question during the talk already, so do you still want to ask your question? Or good? No, it's fine. Another one. Or three. Okay. So that should work. Yes, you should speak directly in it.
Oh, can you hear me?
Yes.
Oh, okay.
Yes.
So I have a question about how this could work for cases where there's a lot of pre and post processing going on, right? So your actual prompt doesn't get to the model the way you think it gets to the model. Yeah, and then the response from the model is also not what you get directly, right? So is there a way to sort of do these evaluations knowing that there's some other set of steps happening before and after the generation? Yeah.
So you mean you don't know if the hallucination could come from the large language model itself or from
the processes around it. Yeah.
I mean, if your goal is to just detect the hallucination itself, then you can still use these consistency-based methods, right? Because they just look at the output of your response, and then you can do it in the same way and sample it. It should still work. You don't need to have access to the LLM or anything like that. I think the idea of like sampling the response a couple of times, if you want it to be deterministic, and then finding out that it's doing different things, that in your use case would still indicate that something is off, right?
Okay, but I guess in that case, we wouldn't necessarily nail it down to the LLM itself, right? So
because you want to know where it's coming from, you mean?
Yeah.
Yeah. Not so sure. Let me think about it. Yeah, I'll get back to you. I'm not sure, but it's a good question.
Thank you. I get some free socks, but wait, there was a question here.
Hey, a bit of a data AI beginner here. Super simple question. I saw this, you used some kind of, was it Jupyter notebooks on databricks.com that I saw on the screen for those experiments?
Yeah, it was a Databricks notebook.
All right, super cool. I have never used those tools. I'm very curious about. Yeah, I'm probably going to go and check it out.
Yeah, it works the same as Jupyter notebooks, really. I mean, yeah, if you want to use like a free version, I would just go for the Jupyter notebooks.
All right, thanks.
Great talk, thank you. I'm curious if you have access to the LLM to its internal state, if you have any idea about the conventions around when you might not return a response if the probability is like low, if it's high entropy, low like confidence. So say you've got 4 predictions and they're all equally likely, should you even have the model output a statement and then later detect the hallucination versus just say, I don't really know, or here's 3 outcomes and they're all equally likely. So I'm just curious if that's something you've explored in the like space of, you know, instead of waiting for it to hallucinate and then detecting it, instead being like, well, my confidence isn't that high, so maybe I shouldn't push something out in the first place.
Right, so that would be the next step kind of, right? So this is more about detecting them, and then the next step would be mitigating them. This is more complicated. I think these kind of methods work well. For example, if you have like a chatbot and you want people to be able to see where the model was less confident. So for example, here at GetYourGuide, we let the suppliers create product text for on our platform. And we now have an AI tool to do that for them. So they fill in some stuff and then it creates like a whole text in the GetYourGuide branding style and everything. there it is useful for them to see like, hey, this might be wrong though, maybe check that. And then people can just manually adjust it, and then you're not like putting anything live that's wrong. When it comes to mitigating it, yes, of course, it would be better. In this case, what you can do is, for example, create a training data set based on, for example, this self-evaluation where you just sample a lot of these responses and then fine-tune an LLM on it, or in this way, like enhance the LLM based on these self-evaluation capabilities. Was out of the scope of this presentation, though, but yes, that would be a next step. But I still think that there's already quite a lot of worth in just flagging them, that people know, like, hey, maybe check this, you know?
Yeah, for sure. Thank you.
All right, we have 2 more questions, and then for the others, you find Morena after. Oh, you were?
Yes.
Okay. Sorry.
So you gave a very nice example in your demo of the toaster example, where you explicitly asked it to give a hallucination back to you. So I'm guessing in a production environment, maybe you want to flag hallucinations, but not the ones that the user specifically asked for, right? So my question is there a way to flag, so to take the input into account and then only flag the ones where you didn't ask for it to hallucinate, and then you just filter those out somehow?
I mean, just to be clear, I didn't ask it to hallucinate, right? I asked it for an absurd fact.
Oh,
So,
fact, okay.
yeah, so it was still not doing what I asked for. But your point is, I mean, this, yes, it would still work if you, if it's hallucinating, even though you don't want it to hallucinate. Because so what's kind of the basis of this self-check GPT tool is natural language inference, which is a model trained on sets of hypotheses and premises, and then says, okay, this is contradicting one another, or this is supporting one another. So it's not per se, it's not per se only about flagging things that are factually wrong. It's also about flagging things that are contradicting or not supporting. So that's why I also use the example of give me 3 facts about Ronaldo, because I'm asking it for free text generation, right? I'm asking it for something that could be different every time, because the model is not deterministic. But if these facts are still not contradicting one another, then it wouldn't be flagged as a hallucination, which I think is why it could still work for these cases.
Yeah, but if you're asking for it, give me something fake, then you would expect 3 completely different and inconsistent answers, right? And that's still fine, because that's what your input asks for.
Yeah, but then why would you want to flag hallucinations in that case?
You wouldn't, exactly. In this case, you would have a high score saying, okay, these are inconsistent outputs, but these are not ones that you would want to flag, because that's basically what the user asked for.
But if I want the model to hallucinate and I just set the temperature high and I just let it hallucinate, I'm not going to import a tool to detect these hallucinations.
Yeah, maybe we can follow up afterwards.
The solution is more LLM. You just ask it, does this contain factual claims, or is it something to do with opinion or creativity? And
I mean,
yes.
there are plenty of use cases where hallucinations are desirable, right? But then,
exactly.
Yeah, but then that's not what these tools are meant for. Maybe I'm misunderstanding you, but then you don't need to flag hallucinations, because it's not harmful in that case.
We can follow up. I'll let other people ask more.
Thank you. I'm just going to give 1 more question, and then for the other, you can ask later.
Yeah,
Speak closely to
I
the
have
mic.
a question about reference-based validation. Specifically, if you have tried it, and in which scenarios have you tried it?
No, I haven't tried those myself. No, I tried the consistency ones and the self-evaluation, but I haven't tried the reference-based ones. But there are some open source tools out there that are ready to use, so you can try it out.
Thank you.
All right, thank you, Morena. So tonight I'm the host, but I also give the second talk, so that's me. So I'm Stephen Batifol. I'm the host and speaker, which is a bit awkward when you're the host and you have to introduce yourself, but I have to do it. But first, thank you all for coming tonight. It's the first unstructured data meetup we do in Berlin. I was expecting 40 people to show up. We have 240 signups, so thank you all. I'm going to go on slightly different route for this talk. I'm sorry for the people that are very good or used to using LLMs or Gen AI or vector database, you might find it a bit boring. But for the others, which I'm pretty sure you have a lot of, I'm just going to tell you and explain to you how vector database work, basically. Because who has heard about vector database here? Probably a lot of people. Who has used vector database? Not that many people. Who knows how they work? Yeah, actually, pretty good amount. Yeah. Well, I'm sorry for you. I hope you still learned something. But then after that, we have an amazing talk from GenAI about embeddings. So you may go for this one. First, who am I? I'm Stephen Batifol. I'm a developer advocate at Zilliz. You can find all my socials here. If you have any questions about the meetup, about anything about vector database, GenAI, LLM, feel free to send me an email. Feel free to contact me on LinkedIn or Twitter. You might don't know who Zilliz is. We created Milvus. We are the creator and maintainer of Milvus, which is the open source vector database. Our whole thing is using open source and creating open source. So we don't only have Milvus, we also have Nowhere, which is a search engine. We have GPT Cache, which you might have used for semantic caching. We have some benchmarks, which are open source, sorry. On top of that, and how I get paid is our cloud offering. So that's where we have optimized Milvus, which is like our self-hosted. And then you also have different things, like you have Zilliz pipeline, so you can put your data there. I don't get paid for that, so I'll only talk about open source tonight. Anyway, we were created in 2017. If you probably don't really know us in Europe because we're California-based, but we have a couple of customers. Our whole thing was to create a vector database that scales, and then you can use us and see it yourself. But those are using Milvus. We also partner with different industry leaders. The usual, what we do as well, which is a bit different, which is collaborating directly with chip manufacturer. So NVIDIA and Intel, we collaborate directly with them. So when you use Milvus, then you can just benefit directly from like NVIDIA Kagra, which is a GPU index based, or Intel as well for like some very specific Intel chips. So that's what we do. We also work with them. All right. That's it about the sales pitch. Now it's about the content. So yeah, Vector Database 101. You might wonder why Vector Database? And one thing is that, you have unstructured data kind of everywhere. It's like, according to some website, it's 80% of the data. And the way Vector Database are different from the usual like SQL, NoSQL database is that, you have your usual SQL database. The search pattern is going to be like select star from your table, and you want an exact result. For vector database, what you're doing is you're doing vector comparisons. So that's like a very different thing. And we are like pretty good at that. We're like pretty good at comparing vectors. And yeah, the vectors, and I'm going to go into more details later, but they are like representation of your unstructured data. And basically, they're just a long series of numbers. Yeah, we're like built to work with text, images, videos, audio, anything that is unstructured. As long as you have deep learning models, then we're happy. So yeah, traditional databases were built on exact search, so like really like on keywords, but they might miss the context or the semantic meaning or the user intent, and that's like something you might struggle with. So if I search for apple, do I search for apple the fruit, or do I search for apple the company? If I search for rising dough, do I mean rising dough, or do I mean proofing bread? If I search for change car tire, what do I mean? Is it like a way to how to change a car tire, or is it when should I change a car tire? So those are like the problem you have if you use direct keyword search. But there's also more. She is a superstar. That's Taylor Swift in 3 out of 4 pictures. And basically, you can see that one is not Taylor Swift, that's the second. And that's kind of how vector databases are working. They're just going to look for something that is very similar to your query. So we do it ourselves. We have a brain and we're like, oh yeah, like we have 3 pictures where they look extremely similar. The 4th one looks a bit similar, but it's not exactly the same. And that's basically how vector databases are working. But where do vectors come from though? Because, we all talk about vector database. We all say like, yeah, you should use vectors, blah, blah, blah. But like, how do you get them? So you have usually your knowledge base, which is going to be like some text, some pictures. If you work with RAG, it's going to be internal documents. And basically your data gets passed into a deep learning model. And what's very important is that this deep learning model it has to be the right type of model. Like it has to be trained on the right type of data. Let's say if you're working with images, you probably want to have a model that has been trained on images. If you're working on text, it's the same, has been trained on text data. If you want to identify type of dogs, then you might want to have a model that has been trained on that. And what happens is that you take your image data, for example, you run it through a deep learning model, and then you cut off the last layer. Because usually the last layer is the one doing the prediction. And you don't want that. You don't really care about the prediction in our case. You want to know what the model has learned, like what it has learned about the data. And really, we don't care about the prediction. And that's basically why we cut off the last layer. And then you have vectors, and you put them in your vector database, like Milvus, please. And then usually, then you have like embedding models. And just want to highlight this point. Those are extremely important, and that's exactly the same where, let's say you're gonna work on RAG, and your RAG is gonna work on text data, and if your text is in German, well, your embedding models have to know about German, they have to be trained on German. And you might have seen me doing some demos of how I chat with the Berlin Parliament. I'm using GenAI embeddings, which are very good in German and English, because they've been trained on both. And so that way, then I can, they understand the German text, and I can talk to them in English. And when I do the demo, I also use OpenAI embeddings. And they're not as good with German, so they really struggle. And you can really see the difference, and that's how you know how important it is to have the right embedding models. You have a lot of them available. You can check it out on Hugging Face directly. And then depending on your use case, you have to find the right one. And it makes a big difference. The different use cases on our side. So I guess everyone has heard about RAG, or most of the people here, which was the very popular one last year. Now it's still popular, but it's getting a bit out of fashion. But then it's not the only use case. You also have recommender systems. That's, at least on our side, that's the most popular one that for people running Milvus in production. Those are recommender systems. Then you have text, image, similarity search, video similarity search, audio, molecular similarity search, which is still something I find very cool, which is you work with proteins, for example, you want to know which proteins are similar to the one you're working on, or when you create drugs, new drugs, that's usually what you may use those, and those are really, really cool. Anomaly detection is also another one. It's very important when it comes to fraud detection. And then the new one, the new cool kid in town, multimodal similarity search. That's what at least people working in the vector database GenAI world, we all talk about that now. And actually, I'm going to talk next month about it, so you may come and see it. But how do they work? That was the talk. So here is an example entry, and on this example, you have two things that are very important. You have the ID, and you have the embedding. And those two things, the ID is the way the vector database is able to have a unique ID in your entry, and the embeddings is what we compare when we go and search. And so the embedding is really what's really important. And then we also have a bunch of metadata fields, which you can also filter on those. Let's say you want to, I don't know, you only want to filter on publication towards data science. Then, you don't want to go through all your embeddings, you can just filter through that first. And yeah, this is an example of a demo app for chatting towards data science. And so what matters, the ID and the embeddings. And the embeddings, they just, it's impossible to know what they mean, sorry. What the values you have are just values that they have been learned, it doesn't mean anything. But yeah, and then, I'll talk a lot about search, and how it works is that everything is based on similarity search. So, at the beginning when I was saying, hey, NoSQL data or SQL databases, sorry, are really looking for an exact result. We only go for similarity. We only go for search for similar things. And that's kind of how it looks like. So that's an overview that's coming from NVIDIA directly. But you have your embeddings coming with your request, which is your query that has been then transformed. And then you just look for the most similar ones. And you can see the first one is very similar to your request. And then this one as well. And the other ones are very different. So you don't really return those. They're going to be very far in the ranking. And this is what a vector database does for you, basically. And then, we're going for math here. I have a master's degree in math, but I forgot all my math. I can barely add now. But anyway, this measures the distance in space, and you have basically 3 different metrics for vector databases. Try to go for the one, like as a rule of thumb, try to go for the one where your embedding model have been trained on. So if they've been trained on Euclidean, which is very unlikely, might go for it. If they've been trained on different metrics that we'll talk about later, go for those. They make your life easier usually. That's the usual rule of thumb. But that's measure the distance in space. So it's basically measure like, imagine like my face and my screen, that just measure the distance between the two. We don't really use that one for deep learning. We mostly use that one for like most like other encoding methods. But yeah, keep that in mind. That's the Euclidean. It's handy, just measure distance in space. We then have inner product, which is a bit more complicated than that. So it measures the projection of one line into another. And then the bigger the angle between the two vectors, the smaller the inner product. We go back to like when we studied math for the people that did. And then we were like, yeah, that's cool, we have sums. But that's the inner product. And it measures the difference in orientation and magnitude. And L2, the one before, is just magnitude. This one, if you work in NLP, you've seen it everywhere, cosine, so it measures the orientation. And it's a difference in angle between two vectors. And so, yeah, you measure how big the angle is between the two vectors. And what's good about this one is that it's not affected by the size of the vector, but only by the angle between them. And this one is mostly used in NLPs. And might have noticed, but cosine is a normalized IP, so normalized inner product that we had before. So if your model was trained using cosine similarity, you can either use cosine similarity as your metric, or you can normalize and use the inner product. And yeah, basically that's it. Those are like the 3 important metrics. They all have the same rank order, but then they just differ in use cases. Then you have something else, which are the indexes. And that's the way you store, the way you reach your data. And you might have seen all vector databases companies being like, hey, I support 3 indexes. Hey, I support 4. Hey, I support 10. Basically, you cannot all fight for that. But then you have 2 or 3 that are very important. The first one is IVF, inverted file index. And it's the most intuitive one, I would say. Basically, you do a bunch of k-means, and then you have some numbers that are the centroids that you can see here, and then you just cluster them, and then you find all of the vectors that are closest to the centroids, and then you create clusters, and then it looks like that when it's pretty. And then what happens during search time is that you search through those centroids for the closest one, and then inside, and then you search the actual points. Then this one, H and SW, which I always struggle to pronounce. This is a graph index, and it takes all the points in your vector space and inserts it into a graph. So it works very well in the way that it's very fast. Recall is also pretty high. The only problem is that it takes a lot of space. But this is the one that's usually like everyone is using at the moment. And yeah, it's very accurate. But the trade-off, it actually takes a lot of space, and because like everything is stored, so like all your points are stored. But usually it's pretty nice. And when you insert, you always try to find the nearest neighbor, and then you just create a new node, and that's how it works for H and SW. Sorry. Then, if you want to be fancy, and I don't really have an illustration for it, but there are like different kind of indexes. A new one that was released by NVIDIA a month ago is also like GPU index. And that's probably the best one you can think of. You just need a lot of money. But it has the best recall, it has the best accuracy. It's the fastest even on small batches. You can see the benchmark here. And yeah, you just need to use H100. So if you are very lucky to have H100, and if you have a lot of money, then maybe you can go for those GPU index. But that's just to tell you, like you have a lot of indexes, and then depending on the index, you will have very different results. You then have quantization, which is like scalar quantization. Like you can think of the way of like bucketing, you know? If you have values that are between -3 and 3, and those are reals, then you want to transform them into integers. So like, let's say you go from like your values from -3 to 2.5 are -3s, -2.5 to 1.5 are -2s. And that's like really good. That's really good to save space, but then you lose accuracy. So then, you know, everything is a trade-off. Then you have vertical quantization, which is square quantization, but across the entire index. So it's not just one vector, but it's horizontal and vertical. And I had a reminder on my calendar, so that's cool. But then what it does, that it saves a lot of space, and that's very useful when your index size is going to be like quite big. We're talking like 20 gigabytes or something, which means millions of documents. Milvus, we offer the way to combine product quantization and scalar quantization with different indexes. So then, yeah, at one point when you reach like 20 million, 50 million, 100 million documents, you might want to go for those because otherwise your index will be either too big or then you might be too slow as well. So yeah, when to pick an index, you have that's just like a quick summary. But if you want 100% recall, use flat. If your index size is like between 10 megabytes and 2 gigabytes standard IVF, then you can use HNSW for like 2 gigabytes between 2 and 20. And then 20 and 200, that's when you want to have like probably a composite index. And then at one point you also have disk-based indexes, but that's like a whole other thing. It's like, what's good is that, yeah, you'll save a lot of space, but they're a bit slower. So then you just have, you know, like everything is a trade-off. But then, yeah, basically just pick an index before, depending on how big your index will be. Index size, sorry. And yeah, how are we different? I won't go into too much details because then it's a bit boring. But like SQL and NoSQL database, usually not very good in high dimensional spaces. Same for, you know, like for searching vectors is a very different thing than to like search for equal results. And then vector stage library, I really like them. I use them a lot when I need to do POCs. But you might struggle when you take things to scale. So, you know, like, I don't know, let's say you have to do a lot of upsets or you have to delete a lot of data, then it's like, you're going to have a lot of trouble. And that's basically why vector database exists. And yeah, we support all of that, but I won't go into that. Just think, yeah, maybe if you reach some scale at one point, maybe don't go for like a library because you will struggle with then you will become a vector database yourself. That's kind of it. I won't go into the architecture, but basically that's everything we have. So we're quite big. And that's it. Any questions? Thank you very much. Meetup May 7th if you want to join. Thank you. Oh, you already have the microphone.
Of course.
Perfect.
I'm prepared. Yeah, my question is quite simple. Could you please provide an example of a query? Because,
yes.
Yeah,
it's
natural language or specific SQL-like language.
So I'm going to take another question. I'm going to try to start my demo in the meantime, right? You can throw the microphone at anyone. Anyone has a question? Oh, right next to you. Don't throw it to them.
How would you turn a couple of thousand PDFs into the embeddings?
So usually, so I have another one which is like talking with the Berlin Parliament, which is actually getting PDFs into like transform the PDF. So it really depends. There are like different ways to chatting with, like to getting data from PDFs. Either you use OCR or then you actually read the PDF through it. And the way I've done it is that I use Llama Index. They have a PDF loader. Mm-hmm. Then you get your data, you extract your data, you chunk the data, you put it in through embeddings, and then you store it in your vector database. And then that's it.
Thanks.
You're welcome. I have one in the front, or like right here as well. Good job.
Yeah, thank you. So basically, when I made my experiments with RAG, and this is when I got in touch with vector databases, virtually none of these tools I used had the ability to delete or to update a document in the or better to say its embeddings in the database. Is this a particular difficult thing to do, or?
Yes.
Okay.
Yes.
So
basically the way, for example, the way we do it is that when you delete like a document from your collection, then we do a soft delete, and then we're just going to be like, hey, don't go there and everything. But then at one point you have to rebuild the index.
Yeah.
Because it's graph-based for most cases. So then you have to rebuild everything, and that's the very complicated part. And so that's why then you have vector database basically. Otherwise, you would have to do everything yourself. You have to redistribute everything and to rebuild everything, and then that's not the easy part.
Yeah, exactly. So if you have quite a complex RAG, that means you have to really index everything again.
Yeah, but then it just depends on you have to pick the right index. Some indexes are really good at being fast for your query. Some are going to be better at upsetting or inserting, deleting. So then you have to pick the right one. Okay. And the way we do it on our side, if I go here, we basically have segments, and we have sealed segments where your data doesn't really move. And then you have other ones which are fresh data we'll go into. And then also deleted one, then we'll be like, okay, most of these segments have been deleted. Let's create a new one with new data. Let's redistribute everything.
Mm-hmm. Okay.
Hey, very good talk.
Thank you.
I'm trying to build a mental model of vectors. So am I basically correct in assuming that you basically pick the number of dimensions you want yourself? So say that I don't know, want to build a database of pictures, then I choose maybe 2 or 3 metrics. One could be indoor versus outdoor. Another one could be temperature. Another one could be brightness versus, brightness. And then these are essentially the 3 dimensions for all items in the database. Is that how it works?
Yeah, so usually when you have data, then you have your data that is text. You're going to put it through an embedding model, and then you have to use the same dimension as the embedding model. So in my example, where I talk with the Berlin Parliament, is that the question you asked? Okay, so when I talk with the Berlin Parliament, for example, I use GenAI German-English embeddings. The dimension is 768. So then in my vector database, I have to create 768 dimension. A vector of 768 dimensions.
But can you choose the dimensions yourselves?
You can if you go train a new embedding model and everything. Yeah.
Okay.
If you just use one, then you have ChatGPT. I don't remember what's the number, but yeah. Then if you use a pre-trained one, then you have to use them.
So you could, in theory, basically have I don't know, millions of items of media, be it text or audio, images, whatever, video. And then you say, for each one, I want to have 100 dimensions. And then you pick one algorithm per dimension, as long as it outputs a number between 0 and 1. Is that how it?
Not true.
Okay.
We can talk about that after if you want. So just to make sure I understand the question correctly.
Yes, I'm coming at this from a very beginner perspective. So
no worries.
All right, thanks.
Thank you.
Next.
Okay, one last one, and then do the quick break.
So you showed a couple of distances, how to measure distances between vectors, like the Euclidean cosine similarity. Do you have some intuition, like which one to choose? What is the effect of choosing one versus another?
It's that for example, your search query might, your results might not be as good as if you had to use the right one. And the rule of thumb I give usually in the one I use is that I just go let's say I'm using an embedding model and it's been trained with cosine metric, then by default I'm going to go with cosine. Or then it depends, you can see it I don't remember which one, but on some of them they really say hey, this has been trained with cosine metric. So usually by default I would just go with the same one. You might have some cases where it doesn't work or something else work better, but by default just go for that one.
So it's more empirical. It's not like you have an intuition, just test it and
cosine,
see
for
which
example,
one.
is better with NLP. So then it also depends on the use cases.
Okay.
Thank you. All right, let's go for our last talk of the evening. So the last talk of the evening is from Bo Wang, which is here. He's the engineering manager at GenAI, where he leads the machine learning team focusing on enhancing search capabilities. Previously, he contributed to GenAI embeddings, cutting-edge text embedding models, and FineTuner, which is a cloud platform for fine-tuning embedding models. He earned his master's degree in computer science from Delft University in technology in the Netherlands. So welcome on stage, Bo.
Thank you. Just test a little bit. Okay, good. And hi, everyone. Thank you for having me here. Today, I would like to give you a short introduction about the GenAI embeddings. Probably a lot of you have already used embedding models or vector database. And in this talk, I'm going to tell you how these embedding models are trained and why we are training such embedding models. I'm Bo Wang, you can just call me Bo. I have been living in Europe for like 10 years. And this is my third year in Germany. And my previous like 5 or 6 years was all in Netherlands. And currently I'm leading the model training team at GenAI. And since we released the GenAI embedding v2, basically we received a lot of hypes in the past months. So GenAI embedding v2 has been trending on #1 for 1 week on Hugging Face. Now it has received over 3 million downloads on Hugging Face. And it has been integrated into a lot of frameworks and vector database, such as LangChain or Llama Index. And also a lot of people are discussing and debating on the Hacker News. We became the Hacker News #1 discussion points for like 1 day or 2 days about long context encoders. So now I'm going to tell you a little bit more. But behind this kind of a lot of hypes, actually GenAI has been developing embedding model for around 2.5 years. So at that time, we are pretty much silent. No one just realized us. And this is my next section. So from fine-tuning to training embedding models at scale. So we basically started to train embedding models since like 2021 or 2022. And we basically developed a framework called fine-tuner to fine-tune embedding models. At that time, it was like same time as the release of Sentence Transformers 1.0. If you know that Sentence Transformers basically became the model hub of embedding models. And we believe at GenAI, we believe that embedding models will be the future of search. And the quality embedding models will determine the successfulness of the future of vector search. So we really need to work on the high quality embeddings. So we started to work on the text embedding fine-tuning, vision embedding fine-tuning, and cross-modality embedding fine-tuning, such as clip models. Maybe some of you know that. And with fine-tuner, we try to solve the problem of using small amount of data to achieve big amount of improvement. So you can see a table here. So basically, we try to fine-tune different kind of models. With here, you can, in the left column is model, actually it's what we call foundation model. It could be the BERT, or it could be ResNet for vision similarity search, or clip models, or multilingual clip models. We even support 3D mesh fine-tuning. And after a small round of fine-tuning, you can see the delta value, how much improvement the original pre-trained model compared to after fine-tuned like model. So from the algorithm perspective, it works. But from a product perspective, we didn't success. So we actually failed. And this is something we realized during the last year's Berlin Buzzwords. So it's like a search conference. We realized that the industry, not even the search industry, they are really slowly moving towards vectors. They just started to use the pre-trained embedding models, such as the sentence transformer embeddings, such as mini-LM, MPNet, or such models. And the industry is not ready for fine-tuning embedding models. And there, at that point, there is no like RAG, or there is no large language model. No one knows what is embedding model. I think maybe vector database was not that hot topic like 2 years ago. So since we believe that embedding will be a success in the future and not right now, why we started to think about, why don't we train embedding from scratch? Why don't we train our own embedding models from scratch? That's the point of GenAI embedding v1. So we started to train GenAI embedding v1. So we basically started to research the state-of-the-art embedding models, such as mini-LM, MPNet, Sentence T5, GTR, and Unstructured. This kind of embedding models mostly from Microsoft, Google, or these kind of big companies, also a little bit from Cohere. Then we collected around 2 billion records of English training data. So it's really a lot amount of data. We basically engineered around 2 months to get this amount of data. Then we did a lot of engineering heavy data cleaning, instead of including the deduplication, language detection. So we only keep the English training data. Quality filtering, so we filter out the low quality like training data. In the end, we basically filtered out most of the training data from our 2 billion like records of English sentence pairs. And we result in around 400 million high-quality pre-training data, and also 5 million lines or records of high-quality human annotated fine-tuning data. We also completely refactored our code base from fine-tuner to support distributed tuning, because previously we are fine-tuning embedding models. In the most cases, 1 GPU should be sufficiently enough. But now we started to support multi-node distributed tuning. And afterwards, we basically published our GINA embedding models. This is the first technical report we published 1 year ago. And this is basically the first paper about GINA embedding V1. We try to build our reputation in the research and also the industry. And after that, where do we go? So we are thinking about we can never stop from here. So basically, from the moment we started to train embedding models, we are targeting the OpenAI level of embedding models and the quality. So we want to train the best embedding model in the world. And we see 2 improved points from now on. So the first one of all, our V2 model, we will start to train GINA embedding V2. So first of all, our V2 model should perform well on the MTB leaderboard. So if you didn't know, MTB leaderboard is basically a leaderboard try to measure the quality of embedding models. But now it has been cheated. We come back to this topic later. And the second, not by me. The second objective is that we want this embedding model to handle longer sequence lengths of data. So at that time, only the OpenAI ADA embedding 002 can handle 8,000 tokens. And we want to beat ADA embedding 002 from the both quality and the context length perspective. That's our objective. So you might be wondering why most of the embedding model can only handle 512 tokens. That is because almost all the embedding models are fine-tuned or continue trained from a foundation model. Most of these foundation models are like BERT or its variations, such as T5 architecture. And this transformer architecture takes the token embeddings or word embeddings from this model at once, then send to the model, send to the transformer block, rather than sending them sequentially. So this is very important for the model to know the word ordering information. So sorry, there is a typo. So word ordering information is basically kept in a transformer layer called position embedding layer. And here is basically something I made a screenshot from the BERT paper. So if you look at here, to speed up the pre-training of our experiments, we pre-trained the model with a sequence length of 112 tokens for 90% of the steps. And then we train the rest of the 10% of the steps of a sequence length of 512 to learn the position embeddings. So the BERT model trained around 10K steps on the C4 dataset or the books corpus to just learn the word ordering information in this position embedding layer. That's why the BERT model can only handle 512 tokens, because beyond 512 tokens, the BERT model never learned that. So here is a diagram about what will happen. So on the x-axis, you will see the token length. On the y-axis, you see the perplexity. So basically, the perplexity measures how this model can understand the semantic of the text. So if you see that this is the pre-trained BERT model, if your token length or context length go above 512, the perplexity will just spike. The perplexity is lower, the better, because the model just completely missed out the word ordering information. So the BERT cannot handle the longer context information. And then we proposed our GINA embedding V2, what we called chain short inference long of GINA embedding V2. The chain short is basically we completely removed this position embedding layer. So we don't have this layer anymore, but we replaced with something called attention with linear bias. So this kind of attention with linear bias basically add an additional small tensor to this each transformer block to keep the position information in these biased tokens. And because this is also short called alibi, because alibi is developed for large language models. Large language models are decoder only. And we are training BERT models, which are the encoder models. So we changed alibi a little bit to support encoder transformer architecture. Then we completely basically retrained the BERT. Internally, we call GinaBERT. We trained the GinaBERT from scratch with some SOTA tricks because BERT was trained on 2018 or 2019. So we trained with whole word masking, Roberta recipe, better activation functions, aggressive masking, because previously the BERT only masked out 15% of the tokens. We mask out 30% of the tokens to let the model guess the mask out tokens. And we trained with full 512 sequence length. And of course, we trained with Alibi to make this model to better modeling longer sequence beyond 512 tokens. In the end, we continue training the GinaBERT. We utilize GinaBERT as a backbone model and continue train Gina embeddings v2 on an improved dataset and an improved training recipe without overfitting the MTB leaderboard. So the problem of MTB leaderboard, just like any large language model leaderboard, is people are getting a good looking score to sell their models. So if you just train on some training data which exists in this leaderboard, then the model is likely to get a very high score. But when training Gina embedding v2, we intentionally removed most of the MTB leaderboard data from our training data. So we really want to examine our model quality on the out-of-domain tasks, on your tasks. So you know how this model really performs on your task instead of relying on a so-called leaderboard. And this is a benchmark actually published by Llama Index. I like this benchmark a lot because this is kind of a leaderboard in the wild. So basically what Llama Index guys doing is they basically randomly pick up a PDF file. Then they send this PDF file into large language models. Then they ask large language model to generate question and answers from this PDF file. Then they get a lot of random dynamically generated question and answerings. So in this case, they started to evaluate a lot of different embedding models, such as OpenAI embedding models, BGE large, which is a quite popular open source embedding model, which ranked very high. Cohere embedding v2, Cohere embedding v3, and Voyage AI, Gina embedding small, and Gina embedding base. So if you look at the score here, there is no re-ranker involved in, Gina embedding is a little bit weaker than the OpenAI embedding. But if you plug a re-ranker together with the embedding model, then Gina embedding model really hit the best performance among all the embedding models. So we are quite confident about Gina embeddings on out-of-domain tasks compared to any other competitors. And we come back to this diagram. So this is the original pre-trained BERT. If you go above 512 tokens, the perplexity just spikes because the model just don't have the word ordering information. But if you look at the GinaBERT, the perplexity just remains the same or a little bit lower because we can modeling the longer sequence up to 8K. Then we published our second paper, which is called Gina embedding v2, the 8K token general purpose text embeddings for large documents. And I want to say a little bit what 8K context length mean to you when you are building RAG applications or vector search applications. So there are a lot of different cases. So if your document is always smaller than 512 tokens, so in this case, Gina embedding v2 is just another average embedding model, such as E5 or BGE or any embedding models, or Cohere v2 or Cohere v3, because it can just take the 512 tokens and embed it into vectors. If your document is always larger than 512 tokens, and the relevant information is at the beginning of this document, and you are trying to use Gina embedding v2 to encode a lot more tokens. In this case, Gina embedding v2 is likely to perform worse. This is because the most important information are at the beginning of this document, and you are trying to distract this model with much longer sequence. But I can tell you how to fix this situation. And if your document is always larger than 512 tokens, then the relevant information is at the middle or the end of the document, Gina embedding v2 could really boost your search performance because no other models can handle such long sequence, and the relevant information is at the end of your document. So keep in mind that Gina embedding v2 just offer you the flexibility to go beyond 512 tokens and adapt your personal need. At any sequence length below 8K. So imagine you want to encode, you are working in a news article company, and you want to only care about first 2K tokens. What you do is just you load the model with Hugging Face transformer. You need trust remote code because we developed our own GinaBird, which is not an official part of the Hugging Face transformer architecture to support longer sequence. And when you are doing the embedding, imagine here is a very long news article. You can just pass max length equals to 2K. So in this model will only take care of 2K first tokens. You can even say like max length equals to 513, which is 1 token beyond any other like embedding models. Just try to encode 1 extra token. Yes. And after we release the English embedding models, what we want to do is we want to do another kind of innovation because no one has done this before. We want to do something we call bilingual embedding models. So what we call bilingual is because we see a lot of so-called multilingual embedding models exist, but they are using a very skewed set of training data. Most of the training data are actually in English. I will show you later. But we want to make a bilingual model, which is good modeling English, modeling an additional language, and modeling the cross-lingual capability between these 2 languages, such as German. So if you look at here, I have 2 pie charts. The first one is a very popular multilingual model called multilingual E5. If you look at the training data of this multilingual E5, it's actually 91% of the training data is English. Then 4.2% of the training data is Chinese. Then another 4.3% of the training data is so-called others or multilingual. We don't believe this will work actually for this different kind of local languages. What we did is we trained something called Gina Embeddings v2 based German. So it utilized exactly the same architecture as the Gina Embeddings English model. And the data distribution is very perfect, beautiful, 50-50. So we have 50% of the English data, 50% of the German data using the linked data pipeline as we designed before. And there is actually not exactly correct because there is also like 3% of the training data are cross-lingual data. So you can imagine left is English, right is German. We want to improve the model capability to understand the similarity between 2 languages. So half English, half German. And we made some comparison. So if you look at the first model, this is kind of very popular model on sentence transformers, multilingual model, but it's also a little bit old. So the size is actually quite small. The output dimensionality is 768. On the German to German search tasks, basically this is a kind of internal benchmark we evaluated on 8 tasks. We basically aggregated all the scores. The score is 41.11. The German to English score is 47.51. The second one is the so-called multilingual E5 large, which is the model in the pie chart before. So it's actually a quite large model. It has 2.24 gigabytes, and the output dimensionality is around 1024. So you see the model performance is 52 and 77. So you have Cohere Embed v3 is another multilingual embedding model. So here they have 2 models. One is v3 English and one v3 multilingual. We don't know the size because it's behind the API. And the output dimensionality is also 1024. The German to German search performance is around 52. And you can see the Gina embedding v2 based German, which is around half of size of the multilingual E5 large. The output dimensionality is much smaller than the multilingual E5, but you reach the highest performance, not only on German, but also German to search English and English to search German. And you can basically utilize the Gina embedding v2 bilingual like this. So you just load the model from transformer package. You define cosine similarity. Oh, by the way, we use cosine similarity to train our models. And you load the model, Gina embedding v2 base DE. DE basically means German. And trust remote code equals true. Then you try to encode, for example, 3 sentences. How is the weather today? Wie ist das Wetter heute? What is the current weather like today? And we expect when you compute the cosine similarity between these 3 sentences, they should give you a very similar cosine similarity score. So our model can handle two languages well, not only monolingual, but also cross-lingual. And also we published our third paper of multitask contrastive learning model for bilingual text embeddings. To our knowledge, our model is the first in the world who working on the bilingual models, not multilingual models. And I think this is my last slide about our future work at Gina AI. Basically, we are currently working on Gina Embedding v3 because we realized OpenAI just released their new text embedding 3 large. So we need to catch up again. And Gina Embedding 3 will be extremely fast and memory efficient. We did some internal testing, and Gina Embedding v2 should be 5 times faster and 10 times memory efficient than our v2 model. We did a lot of optimization on the model architecture. Gina Embedding v3 will be multilingual with a much optimized language distribution. So there will be no like 90% of English anymore, but much more like evenly distributed by different languages. And Gina Embedding v3 will be solving real-world problems. This is something I'm really proud of because we have a team now working on a very comprehensive failure analysis on a lot of on our v2 model and a lot of other embedding models on the real-world data. We try to see in which cases our model fails, and we try to improve our training algorithm, improve our training data to fix these failure cases. Gina Embedding v3, again, will be handling different tasks carefully with carefully designed task instruction and task heads. To our knowledge, this is also the first time in the world who training embedding models using such techniques, but I won't release too much now. And Gina Embedding v3 will be chunk-aware and schema-aware. So it should better understand semi-structured data with different perspective of documents. Again, we invented something new called hierarchical embeddings. And Gina Embedding v3 will be ready in around 8 weeks. And if you want to know more about Gina embeddings, just feel free to go to our ginaai.embeddings, and thank you.
Thank you. Do you have questions? Yes, we have one here. This one works? Yes.
Yeah, thank you for the talk. Well, actually, I'm a user of your model.
Really?
And well, I don't understand really the science behind it. I'm more like a practical person. So, but I try to try to take advantage of the long of the sequence length. So, and because I had with my RAG experiments very often a lot of problems with the chunking, that it's tearing the important information apart in the middle. So I try to chunk a PDF according to the chapters. I mean, I have the long sequence length, so no problem. So the big chapters with the big the headings, and it worked surprisingly well. Would you say that I was just lucky, or do you think this is a good approach to use the sequence length in this way?
Yes, this is actually, we also did some internal evaluation. This is the best approach, actually. So what embedding model doing is actually it learns. So actually it learns embedding for each word. Then what we are doing in the end, we are averaging all the word embeddings. So in the end, you get one representation per document. So when you are applying chunking, so which means the embedding will be averaged along a much smaller vocabulary size. And if you're trying to average a lot more, such as 8K sequence, then you are likely to lose more information. So chunking is actually quite good. Our internal evaluation on some like legal data, German legal data, tells us around chunk size of 768 works best on their case, but I don't know your case. Yes, so chunking is really good.
Okay, thank you.
One question here. Yes, let's take this one. You're catching it? Well, you have a lot of beers around you.
Hey, really great talk. I'm curious about the task-aware embedding that you were mentioning. Is it, I think probably the last slide, is it something like, and I think you were also mentioning about like clever routing and all. Is it somewhat like mixture of experts kind of thing, or is it like how different is it? Because you're talking about like task instruction and task heads.
I want to say something about that, but not really now, but it's something like that. But it will be more lightweighted than mixture of experts because embedding models are relatively smaller. Sure. But I won't reveal too much because I know this meeting will be recorded and there are so many competitors.
Sure, thank you.
Good
Thank
catch.
you.
Thank you. Any other question? Oh, yeah. Well, you close. I'm sorry.
What do you recommend to use in conjunction with your embedding model? Let's say I do a RAG with your embeddings and then I retrieve a document, and then I want to ask a question about this document. I would use, for example, OpenAI then in the second step. But maybe you have a better. I mean, does it make sense to do like both steps? Like in the same model in a certain sense, you know what I mean? Because first to retrieve, you need an embedding model.
Yes.
And then to ask a question about the document,
Yes.
you need a general purpose LLM, let's say.
Yes.
So then, does it make a difference whether I use for the first step, let's say GenAI, second step OpenAI, or maybe OpenAI will tell me no, use ours for both. They have a embedding model, they have their own LLM, or what is your take on that?
Yes, actually, I kind of understand your question. Basically, if I understand correctly, let me try to repeat. You're asking which embedding models works with which large language models, or which is more important. Actually, I think people are making some joking about the RAG because people think it's not RAG. This is GAR, G-A-R, not R-A-G. Because what we discovered is as long as you are using a well-trained large language model, such as OpenAI GPT-4 as Anthropic, or the mostly most recent release of Cohere, the Cohere Command R, large language model can always generate as long as your embedding model can retrieve. That is the case. So the key issue is if your embedding model can accurately retrieve the relevant information you want, and this relevant information is sent as a context to your large language model, then the large language model can always generate well. So the most important thing is actually the retrieval part. This is our observation.
And maybe I can actually add on that. I worked with like GenAI embeddings and OpenAI embeddings on German English text. And when I was using OpenAI embeddings, like it didn't give me the answer of the question I was asking it for, which is how many fax machines are used in the Berlin Parliament. And GenAI embeddings were able to give the answer because it actually understood the document that were in German, and OpenAI was struggling. I'm not working for GenAI. I just wanted to give you like my opinion.
Yes.
Yeah. Hey, thanks. Great talk.
Thank you.
So I'm sorry, I have two technical questions and a business one, but if they take too long, I'll just skip them. The first technical question is like, there's like a setup where you have one embedding for both your query and your documents. And then there's also a setup where you have like a separate question query embedder and then like a document embedder. So you like have one model that'll embed the question, like how many fax machines are there in the parliament, and then another one which does the document. So like in your internal testing, and are you kind of in your vision, are you trying to move to like a one model world or still having a separate query and document model?
I think that is a very good question. Maybe you see some APIs or some embedding models allow you to prepend something like query documents such as Cohere API or some other embedding models. I think behind the scenes, this is one model. But the way we train it allow you to add a prefix or you feel that it's different model is something we call instruction tuning. It's exactly the same as large language model. What they do is actually quite stupid. You basically, for example, when you are querying document, you prepend this query document into your left-hand data. And when you are doing index, you prepend the index document to your right-hand data. Then your instruction tune, this model knows which part should be left, which part should be right. Then this model improve on this certain kind of search tasks. So that is something called instruction tuning. We didn't do that because we don't like pre-penned instructions. Also, a lot of people might miss that. But this actually gives a lot of performance boost. So we might include it into GNN embedding v3.
Awesome. The second technical question that I had was, no, sorry, it was such a good answer. I lost my train of thought. The third one is just as a kind of like, I suppose, a smaller player in the embedding space, how do you find the market conditions? How do you find like convincing customers to switch from say like OpenAI to Gina? Like obviously you're doing a lot of work sort of online on Hugging Face to build support, but what has your experience been like?
Business?
Yeah.
I'm completely blind. I think most of the kind of AI companies are very hard to making money. To be frankly, I think we as well. And I think, but we are burning a lot of money because a lot of GPU usage. We rent a lot of GPUs, but this is something we are trying to figure out.
Oh, I did remember the technical question. Maybe is it okay if I ask it?
Go for it.
Okay.
And then the other questions you'll ask me
Okay,
later.
yeah. So the final technical question is, I really find, at least my experience with vector search in general, is that it's really important to get some kind of fine tuning, simply because if you're in the travel space, and I have the sentence holiday in Berlin and holiday in Paris, for some purposes, that's like exactly the same sentence. It's about travel in Europe. For other applications, that's like completely different. So the sort of distance metric that is meaningful for your application tends to be very specific. So, I mean, do you think that number 5 on your list, these task instructions, will be able to handle some of that? And overall, how have you approached that problem?
I think actually, we have something, I don't think so, to be frankly, because embedding models are very known to be, how can I say, domain specific. So when this model see your domain, such as healthcare data, it will likely to just boost the performance on your domain data. And if your training data is kind of out of domain, so the embedding model might be very unlucky, doesn't really work. So you might need a little bit fine-tuning of your embedding models. And on the other side, because you know the talk name is train general embedding models, our data set was around 400 million pairs plus 5 million triplets. This is only English, not even other languages. So we believe our training data cover as much as different domains, but there's still something might be missing. But in general, in this case, fine-tuning is a better way instead of like task instructions.
Yeah, no, I'm more talking about like task-specific distances, because like, you know, holiday in Paris, holiday in Berlin, no good model is going to misunderstand what that means. But the problem is some applications, it's very different, you know, which one I want to show up. Yeah.
Yes, yes.
Thank you very much for the question. Thank you both for the presentation.
Thank you.
Thank you. I think that's kind of it. I think we have a meetup next month at Delivery Hero. I'm just looking for the slide so you can directly sign up. Where I will talk about multimodal, and then Delivery Hero will talk directly about how they use GenAI to generate images, but also how they are careful with the images they're generating. You know, you don't want eyes in your soup, for example. So they will talk about those things. QR code on the right is what I was looking for. If you want, it's May 7th. Thank you very much all for coming tonight. I'll see you again in May, and that's it. Thank you very much.